These birds defy gravity by flapping their wings. These ice boats sailing across the lake are exceeding speeds of 100 kilometers per hour. These young ski racers are flying down the slope at over 30 kilometers per hour. And these fish propel themselves swiftly through the water with their fins. The leaves on this tree are tossed in the air by wind. And these pieces of wood splinter when smashed by an axe. As you can see, all these objects are in motion. During the next few minutes, we're going to discuss the different characteristics of motion and the various forms motion can take. We'll also learn how to use mathematical equations to make calculations about motion. The Earth on which we live, walk, and move is a huge object which appears to be motionless, but it's spinning on its axis at an amazing rate of over 1,600 kilometers per hour. You decide. In this image of a setting sun, is the sun moving or is the Earth moving? If you answer that the Earth is actually moving, even though it looks as if the sun is moving, then you are correct. We do not feel the Earth's motion, but we can catch a glimpse of its effects by seeing the sun set over the horizon. Why can't we feel the Earth spinning? It has something to do with our frame of reference. For example, we know that this truck is moving because the objects behind it are stationary or standing still. The stationary background, consisting of buildings and trees, is called the frame of reference. In most cases, our frame of reference for objects in motion are objects on Earth, as in this plane taking off. This skier is speeding down this race course. He covered a distance of about 40 meters. It took about 7 seconds for him to cover the distance. This skier was in motion. Motion is defined as a change in position relative to fixed objects over time. Time can be measured in units of seconds, minutes, hours, or days. And distance can be measured in English units of feet, yards, or miles. In the metric system, units of centimeters, meters, or kilometers are used to describe distance. The metric system is the preferred system of measurement in science. Some objects have a very quick motion, while other objects have a slow motion. These mountains, for example, are rising at a rate of 1 centimeter per year, about the rate your fingernail grows in a year. This car was speeding, and now the driver is paying the price. The speed limit on this street is 25 miles per hour. But what is speed? And how did this policewoman know that this car was speeding? Speed is defined as the amount of distance covered in a specific amount of time. The term 25 miles per hour is an expression of speed. It means that a car traveling at this rate would cover a distance of 25 miles in 1 hour. You decide. The distance between the town and the lake where you want to go swimming is 50 miles. At what speed would you have to travel if you want to get there in 2 hours? The answer is 25 miles per hour. A car traveling at 25 miles per hour travels 50 miles in 2 hours. As we have already stated, speed is the rate at which an object moves. But how do we calculate the rate of speed? This car, for example, is going 28 miles per hour. While some high-tech tools, such as the radar gun used by police to calculate speed of moving cars, can be used, there is yet a simpler method. If we know the distance an object traveled and the time it took for the object to travel the distance, we can calculate speed. This can be written as a formula where the average speed equals distance divided by time. Let's put this formula to use by calculating the speed of this sprinter. The distance the sprinter is covering is 100 meters. She covered this distance in 11 seconds. How would you calculate her speed? Let's go back to our formula. Speed equals distance divided by time. All we need to do is plug the numbers into the formula. The distance is 100 meters, and the time is 11 seconds. By dividing the distance by the time, we arrive at an answer of 9.09 meters per second. Speed is expressed as a rate, a unit of distance per unit of time. For example, the speed of this train is expressed in miles per hour or kilometers per hour, and the wind recorded by this wind gauge is recorded in kilometers per hour or miles per hour. If we were going to take a bicycle trip, it is not only important to do the trip at a good speed, but it is also important to travel in the right direction. Velocity is the speed of an object in a given direction. Velocity is very important when flying an airplane. Velocity not only states the amount of distance covered per unit of time, or its speed, but it also states the compass direction in which the plane needs to travel. The velocity of large storms is also very important in helping meteorologists predict when and where an offshore hurricane will reach the land. Their prediction can mean life or death for people who need to evacuate from the path of the hurricane. In some cases, velocities combine to create a greater velocity. For example, this plane can travel up to 200 miles per hour. But when it's pushed by a 50-mile-per-hour wind, its combined velocity increases to 250 miles per hour. This river is flowing at a rate of 15 kilometers per hour. The person paddling this kayak is going at a rate of 8 kilometers per hour. The river's velocity of 15 kilometers per hour, combined with the velocity of the kayakers of 8 kilometers per hour, creates a combined velocity of 23 kilometers per hour. This sports car can go from 0 to 60 miles per hour in 8 seconds, a pretty quick change in velocity. Other machines with powerful engines, such as this motorcycle, can also create rapid changes in velocity. Acceleration is the rate of change in velocity, or it describes how fast speed increases. An object like this sports car is speeding up or accelerating. Just how is acceleration calculated? As in computing speed or velocity, we can use a mathematical formula. The formula for acceleration is acceleration equals final velocity minus beginning velocity divided by time. Let's look at an example of this snowboarder riding in this half-pipe. At the top of the half-pipe, the snowboarder's speed is relatively slow, at about 0.5 meters per second. But after going downhill and arriving at the bottom of the half-pipe, the snowboarder's velocity is about 2 meters per second. The time this took was about 2.3 seconds. To compute the snowboarder's acceleration, we'll plug the numbers in the formula for acceleration. Placing the numbers into the formula, we had 2 meters per second for the final velocity and 0.5 meters per second for the initial velocity. Divide that by 2.3 seconds. 2 meters per second minus 0.5 meters per second equals 1.5 meters per second. Take that and divide it by 2.3 seconds, and it equals 0.65 meters per second squared. We can also graph the acceleration of the snowboarder with speed on the left axis and time on the bottom axis. Notice how the line rises. You decide, what do these following things have in common? This car coming to a screeching halt, this skier gradually coming to a stop, and this soccer ball losing speed. If you said that all these things are losing speed or velocity, then you're correct. Deceleration is a decrease in velocity. Deceleration can be thought of as negative acceleration. When the snowboarder climbs the uphill side of the halfpipe, acceleration decreases. While acceleration can be graphed like this, with a rising line, deceleration can be graphed like this, with a downward line. This glass window is hard and solid. So is this rock. You decide, what will happen to the path of the rock when it comes in contact with the glass? As you can see, the rock continues right through the glass, shattering it. While it's slowed down slightly by the glass, it continues its path of motion past it. A similar phenomena occurs when this toy race car flies off this curve in the track. The reason these things occur is due to something called momentum. Momentum is a property of moving objects. The momentum of a moving object depends on two things: the mass of the object and the velocity with which it travels. It's possible to calculate the momentum of moving objects using a fairly simple formula. The formula for momentum is momentum equals mass times velocity. Let's take a look at the momentum of this softball thrown by this pitcher. The softball has a mass of about 0.3 kilograms. The young pitcher can throw a fastball at about 100 kilometers per hour. To calculate the momentum, we multiply the mass of 0.3 kilograms by the velocity of 100 kilometers per hour to get a momentum of 30 kilometers per hour. The moving pool ball collided with the red ball and transferred its momentum, causing the red ball to move. This demonstrates the law of the conservation of momentum, which states that the momentum of an object remains the same unless outside forces act on it. The momentum gained by the red ball is equal to the momentum lost by the cue ball. No momentum is lost, it is conserved. The similar phenomena occurs in tennis when the moving racket transfers its momentum to the tennis ball. The moving racket loses some of its momentum, but the momentum is gained by the ball, sending it in the opposite direction. During the past few minutes, we've explored many different aspects of motion. We've learned that motion is defined as the change in position of an object over time. And we've learned to calculate the speed of an object by dividing the amount of distance covered by the time it took to cover the distance. We also learned that velocity is the speed of an object in a specific direction. We also studied the rate of change in velocity or acceleration of an object, and how to calculate the acceleration of an object. Finally, we explored the momentum of objects by studying the relationship between mass and velocity. Next time you see objects in motion, try to remember some of the principles of motion we've discussed. You just might look at moving things a little differently. Fill in the correct word when you hear this tone. Good luck, and let's get started. Number 1. A frame of involves an object that is standing still. Number 2 is defined as a change in position of an object over time. Number 3, the system is the preferred system of measurement in science. Number 4, speed is the amount of covered over time. Number 5, the speed of this train can be expressed in units of kilometers per. Number 6, velocity is the speed of an object in a given. Number 7 is the rate of change in velocity. Number 8, graph illustrates the process of deceleration of an object. Number 9, the momentum of a moving object depends on of the object and the velocity with which it travels. Number 10, in this picture, the white ball its momentum to the red ball.